All right, so we're going to talk a little bit about column chromatography, and today we're going to learn about that as well. So column chromatography is a method of protein separation. So there's a couple things, and you'll be doing that this week in lab. There's a couple things that are important. There's a mobile phase, and there's a stationary phase. So the solutions that we put in the top here, right, and they'll run through the gel and they'll end up being collected at the bottom, right? So that's going to be the mobile phase. The mobile phase is usually a buffer of some sort, and the buffer will change salt concentration to get the desired results. But remember, it's a buffer because bulk buffers maintain pH, right? And pH maintains shape, right? And some buffers will change pH as well. But so our mobile phase consists of what we run through the gel, right? The gel, the silica gel, right here, is the stationary phase because it doesn't change. That's what the eluent. So the eluent is what runs through. Is stationary, right? And there's a thing called a stopcock right here, right? The stopcock is just a valve that you can turn on and off. Right, and that determines flow. Okay, the process. So the process of separating is called fractionation. Right. So these are fractions of the total amount that was put through. So fractionation. So pretty simple process. The process allows us to separate based on properties of proteins. So standard column chromatography works by gravity. Sometimes we use what are called flash chromatography, and they work by pressure, right? So in an industry, when I want things done rapidly, I'll be using flash or a pressure system to push it through my gel. All right, so let's talk about some different types. So size exclusion, right? So size exclusion we'll be doing this week or this coming week. Separates based on size. And let me zoom in here for a second. If you look at, so our stationary phase is usually made of like a silica gel or alumina, right? But these are the size exclusion beads. And you'll notice they all have little grooves in them, right? And those grooves are of a certain size meant to trap certain size molecules, right? So our molecules of proteins are measured by mass, and they're measured by Daltons. So there's going to be an exclusion size in Daltons. So the beads have grooves. So they catch up to a certain size, right? So the resin beads are the stationary phase, like I said, smaller molecules allowing larger molecules to pass. So when we put them in, right, in our stationary phase here, they may separate, right? So in the smaller beads, if I looked at here, these would be the smaller. Trapped beads, and these would be the larger right, going around the beads. And so as you're going through your process, right, the larger comes out first and the smaller comes out last. And remember, this process is called fractionation, right? So that process is called fractionation. Right? And that's size exclusion chromatography. These are called eluents, right? So an elution buffer is added to flesh molecules. So usually an elution buffer is a salt or something that will displace the proteins that are in those groups. Okay. I moved that. I don't want to. Let me put that back. We can do another type. Type we'll do after spring break called hydrophobic interaction. So if I have a protein, right? So let's say I have a protein, and I've got some alveoli, and then there's a channel protein. The hydrophobic area is usually in the center of the protein, because remember, proteins exist in an aqueous environment, so all the water's on the outside, which forces all the hydrophobic or the repelled by water areas to the inside of the protein. So hydrophobic interaction, we use different salt concentrations of buffers. So the resins resin catches hydrophobic molecules. Right, so here's the important part. So a high salt concentration changed the conformation of the protein. So first we're going to hit it with a high salt concentration. It's going to take that protein and it's going to turn it inside out. Right? So it's going to expose the hydrophobic areas. It's going to change the conformation, expose the hydrophobic areas to the outside. And then my proteins with hydrophobic areas are going to stick to the resin beads. Then everything else is going to run through. The salt concentration is gradually decreased. I'm trying to get my pen back. It's slowly decreased, and that's going to be called the wash buffer. Right? So what I'm doing when I'm slowly decreasing it is I'm getting these proteins that attached, right, which weren't really the ones I was looking for, to flow through. And then finally my elution buffer is without salt. So it's like deionized water or an alcohol solution that will take those proteins and let them turn back around, and they'll just fall through, right? And they'll be the eluate. Right. By the way, Kirk Brown, he's the one who wrote our book. Right. So that's hydrophobic interaction. So hydrophobic interaction separates based and polarity. Right. So it separates based on polarity. We can do ion exchange. So this is going to separate based on charge. Right? It's going to separate based on charge. And we know that ions have particular charges. Anions are negative, right? Cation are positive, right? So if you look at this picture right here, that's called anion exchange, right? So this is, the example given here is anion exchange because it's meant to capture anions. So for anion exchange, the beads are positive. And for cation exchange, this purple one over here, the beads, are negative, right? All right, so this is kind of opposite the hydrophobic interaction. The resin beads are either positive or negatively charged, right? So amino acids are added in a neutral salt buffer so they bind with the resin. So we're not going to add a high salt concentration, right? It's going to be a neutral solution. So a positively charged protein is going to stick to a negative bead, and a negatively charged protein is going to stick to a positive bead. And then I'll increase salt concentration to get it to fall off later. So same thing. My wash buffers are going to gradually increase the salt concentration, and then my elution buffer is going to have a high salt concentration. Right? It's the same sort of thing. In affinity chromatography, so this scribble. This separates the shape or conformation, remember. Okay? So, so in here the resin beads are manufactured to contain ligands. Ligands attach things, specifically proteins. So these ligands often are antibodies. The antibodies are specific for what they want to capture. So they're very specific. So what will happen is we'll stick, we'll have antibodies attached to the sides of a column or the beads of a column, and if the protein matches, it'll just stick in there, right? So, oops, I don't know why that happened. Right. So proteins are eluted by adding another protein with a stronger affinity or changing the pH. So oftentimes we can change the pH because the pH will change the shape of the proteins and they won't fit anymore and they'll fall out, right? So that's usually how we'll do it. So affinity chromatography is very specific to the protein that we're trying to find. Okay. Scalar chromatography. So the chromatography that we're going to do is going to use columns about the size of a pen, right? But in industry, your columns can be quite large. So if you look at these guys over here, they're doing chromatography in a lab. The mobile phase is in these big sterile holding tanks. That's where the mobile phase is. And it's pumped into by pressure. And this is my resin stack here. That's my stationary phase. Right, so different type of system. That's a industry standard system. And they can be about 1 meter in diameter. Right, so 1 meter in diameter is about normal. Anyway, that's about it. I'll talk to you soon.